put off your cell phones and text phones and everything else, because I guess we'll be talking for half an hour constantly. So welcome to the Cisco Network Reference Architecture, Hadoop. My name is Nimish Desai. I work in a Cisco Data Center Technology Group. And my primary focus is today is a big data application architecture, how it relates to network. I also work on a high-frequency trading algorithms and architectures. And also in part, I also do the job of data center architecture. So I just came from the Cisco Live doing the same presentations about what matters to the networks, how it behaves, et cetera. So these slides, there are tons of slides in this presentation. Some of them are hidden, but you can have those hidden slides. It's about network graphs and the proof points, et cetera. I can't talk everything in network reference architecture in half an hour and then take your questions. So my encouragement to you guys is that always ask questions, raise it, so that it becomes a part of the whole conversation and people understand it. And if we still have a time, we'll go through another set of questions, or we can get offline and answer your questions, right? Or also you can send me email, nidesai@cisco.com, if you need further assistance, understanding of workload, et cetera, right? So most welcome questions. The goal of these presentations with the idea of reference architecture is that how do we make Hadoop easier for enterprise? Can we continue using the same networking technology, or competitors' technology? Doesn't matter, as long as we understand that enterprise adapts set of architectures and topologies, whether the Hadoop is amenable to those topologies, what you need to know more about it, right? And so the whole goal is to provide a reference architectures, make it easier Hadoop, characterize the Hadoop applications, and make it available to the rest of the world, right? So let's see if we can do that process. Big data in enterprise, you guys all know about it. This is a reference slide, what we validated with, what's the environment. It's a Apache 20.2, Linux 6.2, 10 mappers, 2 reducers, UCSC series standard Westmere processors. Romley wasn't available at the time we were testing these things. 96 nodes, 2 reference topology. And the key is that we will revisit this reference topology as we progress. And folks who are standing by, probably there's a couple of rooms over there, so you don't get congested over there, right? So the idea is that we will refer this. We characterize different workload, Yahoo Terasort, as well as the Shakespeare's word count. We use that as throughoutly as a standard benchmarking procedures. And those who are aware of Hadoop benchmarking, there's a growing field in the VLDB and other standards body to make the Hadoop benchmark as a standardized work process, like a TPCCC benchmark, et cetera. So one of my colleague, Raghu Nambiar, is chairing that from the Cisco side, and there are others chairing the effort. So the idea is here is that to provide you a good insight, validated architectures. Enterprise network looks like this. It doesn't look like Facebook's 4,000 servers, all one row in a giant soccer field, okay? It looks like variety of connectivity. You value data, you value SAN, you value NAS, you have Oracle, you have a data ingest problems, you have a data mart, you have a warehousing, you have an external WAN connectivity, you have a user interface, et cetera. So the idea is that there is a variety of access layer technology from us and other competitors available. Ours is a little bit more breadth because we are the networking is the bread and butter. So the idea is that how do you fit Hadoop in this? Where does your rack reside, right? That's the question. And the idea is that we use certain set of structure, modularity, and topology. Can we continue using it, right? That's the key idea. And that argues, and this is not a sort of an argument, but I always try to draw attention to the public, because we all read what does Facebook do. It's a very simple UI, data store, and simple process, right? What is the social networking difference between them and enterprise in terms of the processes, technology, et cetera? Data mostly lives in the internet, partially private, very unstructured data, homogenized workload, no SAN, no NAS, few processes, single team. Enterprise has multiple teams, right? Idea is that you go with the scaling dynamics is totally different. It's an application purpose-driven exercise for their architectures, right? If Facebook has a simple exercise of how do we make people talk to each other with the photos or everything else, right? That's their central goal. Enterprise works in a completely different domains, right? You have ERP, you have a record management, you have a video, you have a collaborations, you have multiple channels, multiple data repository, fewer servers doing a fewer workload. So the map looks like a rainbow. The point is the data is private, data is regulated because you have a HIPAA compliance, you have a PCI compliance. Data model is heterogeneous, multiple schema, multiple data model, multiple ingest technologies, etc. Point is, enterprise is fundamentally different, right? So to make Hadoop adaptive is to understand it, that the dynamics, the scale, the integration is different. What matters to an enterprise is that how can I make it easier? How do I develop a risk-assured topologies, risk-certified topologies, validated workload, etc., so they can do their job as a supporting a business rather than a purpose-driven data center, right? So the idea is that these things drives our reference design in a sense that you only produce network that is amenable to the enterprise. I'm not saying that this topology will not work in the social media as well as the others, because most of the biggest network, including Microsoft, Facebook, and others, are using our network switches, but their topology, their behavior, their policy management are different. So copy what they are doing, but do not exactly expect the results that you expect in the enterprise, right? We agree? So again, the same point, two separate sources of data, two separate sources of tools available. How do you integrate together? We believe, and most of the other vendors will agree with us too as well, that it will become another virtualized pod, or just like a virtualized pod, Hadoop will become another application pod, along with the NAS, along with the SAN, along with the other data repository. Why? Because you need to flow data between these disparate systems anyway, and what we are arguing here is that you need to provide a generic platform so that a data movement becomes easier in enterprise network. So let's look at the cluster design. My manager's over here sitting quietly, not arguing too much with me. He has presented this entire Hadoop cluster design at the Hadoop World 6 to 8 months ago, so I'm not going to go into gory details about what matters in Hadoop workload characterization, etc. In a steady state conditions, I will go through a few slides, but then we will dwell deeper into a failure analysis, etc. Brief overview, you have a 3 or 4 phases. You have a ingest arguments, you have a data replication problems, which is where the jumbo MTU makes a big difference, not during the workload process when the mappers are running or reducers are running, not much of a nectar activity during the map phase. Then you have a shuffle phase, a result phase, and result replication phase. So what matters to the network is network activity during the mappers, some activity, some good spike, some bursty behavior, but the biggest and highest impact on the network is when you turn on the result replication factor 3, which is not on by default, but if you value data, if you value your analytics, you're going to triplicate it because you don't want to lose that job over the time if it takes 3-4 hours, right? So the idea is that we ran with the 2 sets of workload characterizations, standard ETL workload, where the data set remains consistent across all phases of the map reduce, right? You have a 10 gigabit or terabyte data coming in, you have a terabytes of map, you have a terabytes of reduce phase or shuffle phase, and the result phase, right? So data set remains the same. Versus in a Shakespeare's or a word count, which is a BI type of a job, you're trying to sift large amount of data to get certain segment of the facts of the data, right? And that means a data set does not remain constant. It goes from 1 terabyte to 10 megabyte, and maybe the results could be only 1 meg, right? Depends upon the question you are asking, depends upon the workload you are developing. So next 3-4 slides is all about what does it look like in a steady state conditions, right? If you look at a graph, this is a little complicated graph. It's a source. This is the one of the node receiving or transmitting the shuffle output, right? So the idea is that mapper start finishing his job. These are all the small dotted lines are the mappers. They sends the data to the reducers. Reducer absorbs it. That's the spike you see for a 1 gig all the way to the 1 gig link saturation. And then there is a drop in activity. Why? Because mappers has not yet finished. That means reducer is twiddling its thumb, doing nothing. So you have a gap, right? Then you have a mappers finishes again. You have an activity. That's why you have a spiky behavior. Same graph, if you turn on the result replications, look at the difference in the density of the traffic pattern you get, right? Higher density, higher spike, much more link saturated utilizations sustained during the result replications. Same debate on a BI workload. What happens in a BI workload? Because BI workload is inherently a reducing functions, the network activity is much more tamed during the shuffle phases, etc. And of course, replication factor will be even less because you have a small amount of data to be replicated for the result phase, right? Then we look at the data locality. This is just another technical point that you will not always find data locally when the map task is running, right? Sometimes you have a mismatch where the data is and the mappers are running, right? So in the Hadoop, you move the data to the mappers, right? So that's the initial data locality spike that you are occurring, right? Not much of an impact, but it's just a technical point that I want to draw across, that there is a data locality movement that occurs during the phase. This is an interesting slide, and probably I will get a lot of tweets or bloggers saying that this guy is smoking, right? Reason is this. A lot of people ask us how many reducers that you should run, right? And if there is only one reducer in the entire node configurations, what's the impact, right? Of course, the obvious impact is the higher the number of reducers, the better the job completion time, right? If you reduce the number of reducers, what happens to the network? And there are three other slides that it says hidden, but I won't hide it just now to give you an idea. That a lot of people ask that if you send a multiple mappers and the reducers is only one and it's pulling data, what's the network impact? People assume that, oh, it's only one reducer, that means I'm going to saturate that reducer, I'm going to saturate the network. Actually, results is exactly opposite. More reducers you have, more reducers are pulling data from the mappers. That means more network activity because it's a many-to-many communications. If you look at the reducers with the 24, you can see the buffer utilization drops from 35,000 cells, which is the cell terminology we use in the Nexus 5K switch portfolio, from 35,000 switch cells to the 5,000. In other words, network is less utilized, buffer is less utilized, right? When you have a number of reducers going down. Typically, there is a debate when we talk to customers saying if you have a badly programmer running job, what does it matter? Reducers ratio matters or mappers ratio matters? Well, that will also be dictated by your workload, but the network behavior, understand it that more reducers means more traffic, less reducers means less traffic. Going back to the network side, which I will work a little bit more, this is the detailed slide, or the rest of the presentation is based on. So we have a hypothesis saying that, hey, there are few factors matters in the network viewpoint. Availability being highest, buffering and the oversubscriptions more or less the same, or data node speed and latency, right? This is our hypothesis. The reason is that we have done the work of testing and we believe this hypothesis is true. So let's dwell into that a little bit in a validated reference architecture. An access layer is made out of a variety of devices. You want to put your Hadoop cluster at the access layer at the top of the rack switch with tons of other compute powers you have, right? So the integration matters. What matters in the network architecture? Architecture matters, availability matters, oversubscription and buffering matters, management and visibility. These are the 4 or 5 criteria that we have currently working on, or things that's important, right? So how many people know Nexus 5000? 1, 2, 3, wow, that's fantastic. So you guys all aware of a Fax architecture. What Fax architecture does is that it allows you to decouple your physical wiring infrastructure from a centralized locations, right? Because then you don't have to run all the cables from all the servers to all the end of the row, right? So the Fax architecture is a fundamental underpinning that you virtualize your layer 1 layer so you can put equidistance any place, all the servers wherever you want, right? That's a common struggle sysadmin runs with the networking guys, because networking guy says, no, I can't give you that cabling plant, no, I can't give you that VLAN, or not, I can't give you that subnet, etc., right? So Fax architecture is important. What else matters in a DC top of the rack DC design, right? What matters? What matters is a architectural consistency. What matters is a risk assurance, a feature consistency, because a operational consistency. You don't want a Hadoop network to be looking totally different than your virtualized workload or Oracle workload that you have, right? That matters because operationally it becomes easier to integrate in the Hadoop network. lots of east-west traffic. The other two keep out. Hadoop will be using a monolithic workload or a multiple workload. Next generation Hadoop will have a HPC type of functionality built into it. So now we will have a diverse workflow. How do you categorize it? How do you create a QoS? How do you create a SLA argument? So the feature and consistency matter that you mattered with the rest of the network and the rest of the application workflow that you were doing, right? 4 sets of design that I can come up with. Single attach, 1 gig dual attach, 1 gig, 10 gig single attach, 10 gig dual attach, and we have a reference combination of portfolio or product that you can use as a reference. So going back to the original slide that I presented in the first part or the first slide of the presentations, we work with mostly a Nexus 5K, 2K topology, and we also validated with Nexus 7K with the top of the rack switch called Nexus 3000, right? Both technology will work for you. Our recommendation is that if you're doing for layer 2 workload that you need it for a virtualized VMware or a Hyper-V or Oracle, most of the customer deploys this, and we set out to ask the questions how good or how bad those topology behaves, right? And we think that will matters most to the enterprise customer, right? So we set out with these dual tier architectures, and the key factor, lots of information about it. You don't need to learn about all the networking geekdom, but the point is redundancy matters at every level, right? There was no PowerPoint, so I had a USB. There was no slide flipper, so I had a slide flipper. So redundancy matters, and at every level it matters, right? The key point for you guys to remember is that at the access layer, you have a variety of choices to connect networks, single attach, dual attach, or active standby. We are working on work with the single attach server characterizations and the dual NIC attached characterization, 1 gig and 10 gig, right? And this is the one of the most adaptable topology for any type of a server connectivity you want, right? So you homogenize, doesn't matter what network topology is or what server configuration is, your network topology is adaptable and redundant all the way. Man, did I bore you? Right, seriously. Now the question of the single node architecture, right? So what we validated is that a failure domain is critical. So when we run a standardized job, one terabyte Yahoo Terasort, in our approximation it takes 4.2 to 4.3 minutes. Then I take a single wire out, Ethernet cable, from a single node. I get roughly double the execution time. Now, that is not sand in stone number, but that's our observations, right? With all the default setting that you get in a Hadoop configuration, all the Hadoop, except few heap size calculation was different, right? But the key observation is that if a regular job takes 4 minutes, pulling a single node takes almost double the time, may not matter much for a interactive job, right? 4 minutes, you rerun it, right? But if you're running a ETL job and it takes 8 hours, our hypothesis or our observation is that you can't afford another 8 hours of pricing calculation. As Sears CIO was talking about, there is a cascading effect that happens when you run this job with feeding to each other modules, right? So the point is, we are talking to Hortonworks as well as Marun Murthy and the Tan Dunning from the MapR, how to make this better. And the question is, this is a repeated slide. This is an example of the job completion time, regular 286 seconds, a single node failure, 1100 seconds. It has a 10-minute dead node detections, right? A data node disappears, name node detection takes almost 10 minutes, right? So 4 minutes, 10 minutes of dead activity, and then another 4 minutes to execute the job. So workload characterization matters. In this case, what happens is, if takes a parallelism, one node goes away, other 4, let's say the example of 5-node example, they are all running in parallel job. One node goes away, other 4 node has to finish his map task and give it to reducers. Until they all finish, the 5th node's map task cannot start because it's already, because you are failing by the way, this failure is introduced in the reducer phase, okay? Reducer phase, 33% reducer completed, 66% reducer completed, and 99% reducer completed. All three phases, I see the quadrupling the time, but it is amplified because you have a 10-minute dead interval. Then we ran the multiple 1 terabyte, 2 terabyte, 5 terabyte, and 6 terabyte job, and we finding it that it's doubling the execution time. We will work a little bit more on this, a little bit with more detail. Stay tuned on cisco.com/big data site, where we will update the results with the probably finding an enhancement or finding a different type of workload that may affect a different characteristic of the node failure, right? Everybody is with me with what I'm talking about? Yes? Agree? Or sleeping? Am I? Okay, good. What else we did? We failed almost every component. 2 key points. We failed the rack, we failed the link, we failed the Fax Architecture node, we failed the Nexus 5K. 2 key points. A single node failure has a bigger impact. Rack failure has certainly a bigger impact on your job completion time. In a rack failure, whether you are a single attach or dual attach doesn't matter, because both of the top of the rack switch fail along with your servers, right? So it doesn't matter. You will suffer some delay in the job completion time, right? Going back to capacity and planning. In this, what we talk about is oversubscription, right? So the debate goes on that you need a non-blocking network. The answer is you don't need a non-blocking network, because we tested it. Why? Typically, the oversubscription matters when your node density goes higher in terms of the speed, right? From 1 gig to 10, you are at 10 times higher speed at the access layer, at the server layer, right? So you have to reflect the similar capacity planning in the network, how many uplinks or how many internodal links that I need to connect to, right? So theoretical throughput oversubscription could be 16 to 1, 8 to 1, 4 to 1, because how many 10 gig attached server you are connecting to top of the rack switch, and how many uplinks from that switch you are connecting to the central switch or anywhere else, right? Point is, still, this entire oversubscription concept is driven by how your I/O is configured, right? How dense your I/O node is. It's always limited by your I/O. So we set out with the 4 spindle ratio, and we said, okay, let's test it. What's the real impact of oversubscribing the network link, and what's its impact on a job completion time, right? So if you look at this graph, the blue line is the 8 links, 4 links, 2 links, and 1 link. 1 link means 1 link being the 1 10 gig link. 16 servers, 16 10 gig servers are feeding to those particular 1 link, right? Job completion time is not varying much, some 30, 40% more time, because you have an oversubscribed link. That means you're dropping packet, etc., right? What's important is that if you turn on the replication factor, then oversubscription problem or oversubscription issue gets amplified a little bit further. However, if you look at the rack failure, it doesn't matter. Rack failure is severe enough that it overshadows the oversubscription factors irrelevant in this particular test that we are doing, right? So the key point I'm trying to emphasize is that oversubscription matters, the degree of oversubscription matters, but not necessarily you need a non-blocking network, okay? Period. So let's look at the 1 gig versus 2 gig versus, or dual attach versus 10 gig network, right? So we charted out the different graphs and its behavior. The first graph is the single attach, and I talked about that before, but with the 96 node, with the latest Apache Hadoop. So you can see there is a constant activity because network is constantly saturated. Mappers are finishing faster than the reducer can consume because it's all 1 gig, right? Moving to a dual attach scenario. In a dual attach scenario, you see the gap. A mapper is finished, and the reducer is pulling this data, and then mapper is still working on, so there is a gap in between the network activity, right? Now, translate that back to a 10 gig. In a 10 gig, the void between the mappers finishing and the reducer pulling is wider. Why? Because you have a wider pipe is available. You're sending the data immediately. Reducer says, I can consume it. Mapper says, I'm not finished yet. So reducers wait until mappers can finish the job, right? 2 key points. A 1 gig attached workload will work fine Dual gig attached load will do better because you want a future proofing. You can see that it's hitting 1.4 gig on a 2-link combined output, right? 10 gig job when we run, what we find a job running much smoother. In other words, I don't get too much variance in terms of the 4 minute 20 second, 4 minute 22 second, 4 minute 33 seconds. Compared to a 1 gig job, I find some variance in it, a little bit wider, like 30 to 40 seconds differentiation in terms of the way job finishes. So do you need a 10 gig network today? The answer is no. Does it help you future-proof? Yes. Are you running more than just one job? Are you ingesting data? You're exporting data? Are you doing some other parallel activity? Do you want a response time that while you're running a ETL job, you want a ad hoc query to be run as well? For those reasons, we recommend you to go with the 10 gig, right? Because you are future-proofing it, you are already saturating the 1 gig, 2 gig line, because the 2 gig you are already hitting 1.4 gig. As the networking platform compared to server platform refresh faster than a networking platform in terms of the infrastructure upgrade costs, etc. So you will have a Romley platform, you have a denser node, and it will guarantee, I will guarantee you it will drive your 2 gig link, right? Then you have a spillover, then you have erratic behavior because now CCP is congesting, etc. So the 10 gig adaptations does matter in that terms, right? What else? This is another interesting observation. What happens in the buffering behavior with the 1 gig attached node or a 10 gig attached node? So if you look at this, it's a complicated graph. You have a multiple mappers running, 1 gig attached mapper, 10 gig attached mapper, and there is a reducer graph. This is a reducer graph. So as soon as the mapper finishes, the reducer graph takes off, right? And the brown lines that I'm showing on the top, those are the 1 gig buffer utilizations. Of course, because there is a congestion is building in the network, buffering is occurring, high level of buffering, compared to a 10 gig buffer level is much lower because the resistance from the network or resistance from the speed is not there, wider pipe. What does that mean? What that means is you need to adapt to the workload with networking in mind in such a way that you don't need a super duper deep buffer switch, or you don't need like a totally no buffer switch, right? There's a happy medium, and we're going to talk about that in the flexibility in the next slide. Multiple workload when you run. What happens to your job completion time? So we run ETL jobs, we run ad hoc jobs. We did a 8-node ingesting with terabyte ingest on an 8-node. We did that, right? While the jobs were running parallel, right? There's around 18% reduction in the job completion or increase in a job completion time when you run a multiple activities together, right? Another key interesting point in the debate that why would a single node execution takes double the execution time? So I said, okay, let's find out what if we run 100 such job, 10 gig each, 1 terabyte total data set, and see what happens. Key observation is the job is completing in average 4.36, etc. minute. But when you fail a node, all jobs, almost all jobs are impacted. In other words, your scheduler is doing a fantastic job distributing the jobs across multiple 96 nodes, right? Still, rack failure trumps it, right? Rack failure has the highest impact in the same case, right? So it's a consistent network behavior, etc. Management and visibility. So management-wise, we have to yet do some more work because we ran out of time in terms of producing the results. So we'll have the white paper will update it a little bit more management visibility in terms of the how many flows, how it behaves, what's the thick flow versus transient flow, etc. Visibility viewpoint, we argue the point is that the buffering viewpoint, you need a consistent buffering scheme. You need an adequate buffering scheme. This is not a trading floor architecture where first packet matters. It's TCP for God's sake, right? That means you can tolerate some congestions, you can build the elasticity network, you need an optimal buffering, and the point with is that you also need to know changing workload will force you to say, okay, what's happening in my network? So we are providing a visibility into the network architectures and the buffering schema with a set of commands and configurations so that you can adapt your workload and change networking queue based on your observations, whether the network is being dropped heavily or not, right? Wow, that's interesting. My graphs went away. That's odd. Okay, well, I will update this graph, but if you remember what I'm talking about is that a buffer, this is a characterization, the same buffer utilization characterizations I did before over here. Just a second. Where is that? This. Similar to that, we did a graphing of a Nexus 5K, 2K architecture buffer results, and we compared that to a Nexus 3K results. And results are more or less the same, right? The granularity is a little bit more in Nexus 3K, and we are working on improving that granularity in the other architecture as well, right? So the point is that a buffering is needed, buffering is useful, but you absolutely don't need a deep buffer switch in order to execute your workload. Another key point, latency. You application folks do not need to be told that how slow is Java. Okay? Compared to that, networking latency is absolutely nothing. All right? Consistently, if you increase the data set size, you will increase the latency, but not that much, right? Because if that would have been the case, if latency mattered, then my job would have finished faster with a 10 gig network. I cannot share that data with you because I can find a noticeable like 30, 40, 50% difference in the job completion time with 10 gig, right? Maybe Hadoop framework needs to be a little bit more optimized in terms of the yarn, or Hadoop 2.0 will have a different behavior, and we'll revisit that next year, et cetera, right? But the point is, consistent latency matters. Application latency and the DNS latency that your Hadoop node has to go through is much bigger, right? What's the key point? The point we are making is that we need to make the Hadoop adaptable. We need to make networking adaptations for the Hadoop simpler. You can adapt the existing network technology for Hadoop. It's much simpler, much easier, and we have given you that characterizations. And then I'm not going to repeat all the summary points, but the 2-3 key points I do want to emphasize. Look forward for 10 gig architectures because it has a future-proofing advantage. Dual node behavior seems to be favoring to the Hadoop workload compared to a single attached workstations for the servers. Oversubscription does matter, but you don't need a non-blocking network. And finally, the latency is not as important factor compared to other workload that you have in your enterprise, right? We have this white paper already on, I'm not talking the 100% detail that I'm talking here. We have a white paper that characterizes Hadoop workload at cisco.cisco/go/big data. We have a Jacob Rabb's presentation at Hadoop World Summit. You can download it and or listen it, et cetera. And we will update these entire presentations with much more detailed presentation and white paper in coming days, so you have a reference architecture for you to work with. All right? I will now take the questions. Thanks for listening very quietly, and you guys are all awake, so I'm happy. Questions?
What sort of frame sizes were you using with your testing?
Yeah, so the question was what sort of a frame sizes you were using. In this case, in the 1 gig also 1500, but in the 10 gig we were using jumbo MTU, right? And that's the key point I wanted to make in the earlier part, that it's impacting a little bit on an ingest cycle because you're coming from outside. You will again subjected to 1500 byte because if the outside repository is not all 10 gig, you are subject to 1500 byte. But the result replication can be done in much faster, because 3 times faster, because 1500 byte versus 9K moving data at one chunk, right? So, question?
Jian Li, IBM, Nimish, very nice talk. I need to digest your talk in more time. But allow me 2 quick questions. One is, in all your network characterization plots, did you change the overlapping between map and reduce? In other words, the slow start rate ratio of map reduce?
No. So the question is, I will repeat that. He's giving me a great kudos, thanks. But the second thing is that he's asking whether did we do the overlapping variable mappers to reduce the ratio? And the answer is no, because we wanted to keep a consistent mappers to reducers ratio for all the characterization of job. We're going to work on, in coming days, creating a variations on that. And then, because there is a debate on the internal team debate saying like, okay, what if you have a map-only job? job, right? Or what if you have a reduced intensive job versus the mappers job. So no, this was just a static 10 mappers, 2 reducers per node.
But between map and reduce, do you overlap them, or you wait until all the map finish before you start one single reduce?
It's default. No, it's whatever is in the Hadoop 20.2 default. What is it? What's the default? No.
Reduces start along with the maps.
Reducer, yeah, it does starts along with the map.
Sometimes it's 0.05, sometimes it's 0.95, so there's a lot difference. But anyway.
Yeah, ask me question of, probably I'm not following you.
Another question is, so at the roughly very beginning of your talk, you had a chart showing how you, the bar chart showing you see availability is most important, and latency is the least. How did you quantify this bar chart?
The quantification is observation based. It's not a measured data. That's how we started the hypothesis, right? And going through all the workload completion. So the question was, there was a chart that I said, okay, hypothesis is that availability is important, buffering is less, latency is the least important piece. The way I went through the entire presentations, we shared about what happens if a single node fails and its impact on job completion time. What happens if you have a buffering problems, or if you run a heavy replication workload, does it really matters on a job completion time? Linked node speed, whether 1 gig versus 10 gig matters or not, and we are not finding heavy difference, but we are observing there is some degree of improvements in the job completion time. So it is a observational feedback from our testing, right? So measuring from the magnitude-wise, I can tell you that availability is 50% more important than the latency, and latency is the 1% compared to the oversubscription, et cetera. Does that help?
Gotcha. Yep. Yeah. Thank you.
Any more questions? Question? Okay.
Hi, Nimish. This is Pankaj from Infoblogs. Very nice talk. It was very interesting, and we are looking at this research within Infoblog for some of the things. So we are looking. I had a question specific to OpenFlow, the new emerging technology and standards, because a lot of the switching standards, just like Hadoop, has become a commodity. The beauty of Hadoop is everything underneath is a commodity. There need not be any proprietary one. OpenFlow is the open standard, and how do you connect those two initiatives with your research?
The question is, there is an initiative in the networking world called OpenFlow. And how do you correlate to Hadoop? Because Hadoop 2.0 or 2.2 or any Apache project is open. So can you make these two open architectures or open initiatives correlate to each other? And absolutely, the answer is that we will play a part in Cisco Live. This week we announced the entire ecosystem. We are opening up the Nexus OS CLI with the open controller switch format. We are opening up the CLI XML format as well as the open PK development. So Cisco will have a developing workshops. We already demonstrated a Hadoop rack awareness plugin for an OpenFlow. So absolutely, rock on.
Thanks. And one more question. So on the same OpenFlow initiative, there are some open source initiatives on OpenFlow, like Nicira has OpenFlow, vSwitch, OVS, and then we just announced Link, that is our own open source thing. So what is Cisco contributing to the open source community on that?
There was a project called what is the release name? I forgot. Diablo. In a Diablo, we contributed heavily in terms of the routing engine as well as the switch max and the switch designs and the VLANs, et cetera, right? So yes, we are contributing in that. And the second piece that I want to note out is that the behavior of OpenFlow versus what you want to do in enterprise are two different beasts, right? The assumption here is that in the OpenFlow paradigm, you know your application workload, you're doing a top-down design model, and not like, okay, I'm going to buy the best of the breed from the Oracles and the SAP, and because each has to offer unique value propositions. When you do that, OpenFlow implementation gets really tricky. So as the ecosystem matures, And if the Oracle produces some information that we can use in the network and vice versa, the system will flourish.
Thanks. Nice talk.
Yeah, appreciate it. Thanks. Question? No?